terminal window is gone. Is that, you guys have sound? Can you hear me? Is that it? It's good? Good. All right. So when I was pitching this talk, I thought, I'm always told this advice, you should never do live demo in a talk. And then I pitched this to the organizers. I said, I should just do a talk that's all live demo and just see where it goes. So the topic of this talk is, I'm going to talk about threads and coroutines, topics that are pretty active in the Python world right now. And I'm going to talk about it at kind of a low level with the hope of looking at like different trade-offs and performance characteristics and things that can go wrong. So that's kind of the topic. One little disclaimer, I probably would not advise using any of the code that I'm about to write, because this talk is actually done completely from scratch with nothing to start with. So to start this off, I'm gonna start with a very important problem, which is obviously Fibonacci numbers. I don't know why I started picking on that, because I hate it so much as an example, and then I find myself sort of using it all the time here. So what I've got here is a horrible implementation of the Fibonacci number. Okay, so it's a recursive algorithm. It has exponential growth. Terrible idea, but I'm going to use that as just a motivating example for things that are going to come. Oh, probably one other thing about doing a live demo: don't use an alpha version of Python. That might be. We'll hope that doesn't bite me there. Okay, so basically this Fibonacci number thing just computes a Fibonacci number. It has the feature that the larger the number, the longer it takes. So if I put in, like, you can sort of see it sort of noticeably slowing down because it gets longer and longer. I'm actually using that to have like a wide range of computational times that I'm going to use in a minute here. Okay, so you have this Fibonacci number thing. Now that is pretty boring as I have it right now. I mean, you would never want to use a library like that. What you would probably want to do is make a microservice out of that, right? So, Fib microservice. So we're gonna use. Can I call the socket library a framework? Would that make more people use it? Okay. So we're gonna use the socket framework for that. And every good talk is always started with socket programming. So if you've never done socket programming before, I apologize. I apologize on that. This is basically the special magic of socket programming, going into setting socket options. Okay, so what I'm doing here is basically creating a network port, binding it to an address, telling the system to go listen to it, and then I'm just going to receive connections on that. Again, socket programming, sort of 101 here. If you get a connection, I'll sort of print out where it came from, and then I'm going to pass this over to some, I don't know, Fibonacci handler of some kind. Okay, so this is going to be the world's worst microservice, by the way. Okay, so what the handler is going to do is it's just going to go into some loop where I get some kind of request coming across. Okay, so we'll receive that. And then if nothing happens, I'm going to break out of that, and then I'm going to just convert the request into an integer. As I said, this is going to be a really stupid microservice here, and then compute the Fibonacci number, and then basically make a result by turning that back into a string, encoding it as ASCII, and then maybe putting a new line on it. Do I have a bug in there? One disclaimer of this is I probably will have some typos in there. Oh, it's not request? Well, we'll get back to that. Okay, yeah. If not request, the dangers of live coding here. Okay, and then if you break out of there, it's basically closed. Okay, so this is a little network server. I'm missing a few things. I need to import the Fibonacci number function and so forth. So you have that, basically socket programming. And if this works, I should just be able to maybe run this, sort of saying, like run a Fibonacci server on port 25,000. Let's see, do I have another bug in there? Zero result. Oh yeah, okay. You guys are such sticklers here, It's like, As I said, we're going to run this without unit tests or anything. So okay, so let's run that and sort of see what happens there. Okay, so this is running a server, and then if it's working, I should be able to netcat or telnet to that, and just see it respond. Okay, so it's computing Fibonacci numbers and so forth. Okay. All right. That's the boring part. You don't want to clap for that. Okay. So and now the problem with that. Okay. So it's on the network and so forth. The problem with it is that it can't handle multiple clients. Like if I were to try to connect from another window and then do something, it's just sort of sitting there dead because this other client is sort of hogging the connection. If I kill that client, then the other one will wake up and it will respond. Okay, so this is kind of a classic kind of concurrency problem with network programming. Is if you don't take steps, you can only handle one client at a time. Okay, so that's what we're starting with, is basically that. Now, what a lot of people are going to turn to with this, to do concurrency, maybe as a first approximation, is to use thread programming. And so just to do that really quick, I mean, you can import, from Python's threading module, you can say, okay, give me a thread. And then if you want to make this support concurrency, I mean, an easy way to do it is you can just create a thread object where you just say, okay, just run that handler in a thread. And then launch it. Okay, so it's kind of like a one-liner thing. But if you try that and run this new version of it, let's check it out here. Make sure it works. Okay, that's connected, and that one is connected. Okay, so I have two clients sort of connected there. Again, no, there's more to come. Okay, so now. Threads is one of these topics. I mean, I've given talks about threads before. I mean, especially with like the global interpreter lock and so forth. And and one of the results of that is people often say, never use threads. I mean, it's like, they suck or something. You know, there's a lot of like talk about threads in Python. Just some underlying details about that. I mean, Python is actually using real system threads. I mean, threads are POSIX threads. They're managed by the operating system and so forth. But there are some things that can go wrong with them. And some of these are well known due to things like the global interpreter lock. Others are not. So to illustrate that real quick, I'm going to write two performance tests. This first one is more of just measuring the time of maybe a long-running request. And the way that this is going to work is it's going to be more socket programming along with some timing. And all I'm going to do is essentially create a socket connection to that server. You didn't realize you were going to get a tutorial in socket programming coming here, probably. Okay, so and then I'm just going to enter an infinite loop where I just record like a start time, and then I'm going to send off a request for some moderately sized Fibonacci number, like 30 or something like that, and then I'm just going to wait for the response to get back. There's a whole lot of things that I would probably need to add to this to make it reliable, but that's all that's happening here. Okay, so let's do that. I think that will work here. Sock.send. Yes. Okay. All right. So I'm going to send a request, get a response back, and I'm just going to run that. Okay. So let's check that out. Try to run that. So what this thing is doing is it's basically hammering the server with requests over and over and over again. And it's saying, okay, it takes about a third of a second to do that Fibonacci number. Now, one of the things that you know about is Python has a global interpreter lock, the dreaded global interpreter lock. And what most people know about the global interpreter lock is that you can't use multiple CPU cores. It basically pins Python to a single core. And you'll actually see that if I run this performance test twice, so I have it running like in two different windows, all of a sudden you see the times basically double. I have multiple cores on my laptop, but Python can't take advantage of that. It's sort of pinned to the one core. The same thing, if I were to run that a third time, it's now it goes up to like 0.9 seconds. You're seeing Python limited to the one core. So that's one impact of the global interpreter lock. It's just that one core only. Now, it turns out that there's another facet of that global interpreter lock that is not as widely known. I mean, some people know about it, but it's not as widely talked about. And it actually concerns the behavior of short requests. So I'm going to do another little timing test here. The purpose of this is going to be just requests per second of fast requests. Okay, so I'm going to keep the code that I have here. Instead of doing that, I'm just going to keep kind of a global counter where I'm going to send like the Fibonacci number of 1. It's almost instantaneous. And then I'm going to increment that counter. And then, this is a little bit bad, but I'm going to create a thread that just monitors that counter. Okay, so again, it's sort of dumb here. Okay, so what I'm going to do is just do a while loop where I sleep for a second, print out how many requests per second it made, and then just reset the counter. Do I have a typo in that? I hope not. Okay. Okay, let's try that. So what's going to happen here? Let me make sure that nothing else is running. Okay, so this test is essentially just going to hammer the server with lots of requests, like really short requests. So it comes up and it says, okay, I'm doing 25,000 requests a second, 26,000 requests a second, hammering away on the Fibonacci number. So here's the other kind of interesting thing about the GIL. It turns out that if you have something going like that, like really fast requests, and somebody requests something that takes a bit of CPU work, like let's say I come in here and I say, yeah, compute like the 30-second Fibonacci number, you're gonna see like a little, you're gonna see a dip on that. I mean, it's gonna drop down. It's like, oh, 8,000 requests a second there. But if the work sort of increases, like let's say I compute the 40th Fibonacci number, you're going to see the response time of the fast thing drop off a cliff, basically. Okay, so what you're seeing now is it's like 90 requests a second. So down from like 25,000 down to 90. Now, the thing that's happening there is actually pretty interesting. It turns out that one of the features of the GIL is that it prioritizes things that want to run on the CPU. So like it actually gives highest priority to the things that are like chewing away on calculation. I'm not going to go through all the reasons why that takes place. I mean, it has to do with the implementation of the GIL, but that is actually kind of an interesting phenomenon because that is actually not how operating systems do things. Like you know, if this thing were okay, it's back running, you know, doing 25,000 requests a second. If I were just to run like a separate Python interpreter. Okay, this is a separate process, and I were to say, okay, go compute like the 50th Fibonacci number, and come back here, it barely even makes a dent on that. Okay, so the operating system is like totally happy with that. If I were to, you know, launch like another one of these, you know, again, compute the 50th Fibonacci. That's a tough thing to say, 50th Fibonacci number. Okay. Again, it's like, okay, it's now my machine, I mean, it's like really hammering away, but that short request is not really that adversely affected by that. I mean, and the thing that you're seeing here is that the operating system basically gives priority to short-running tasks, things that are interactive and so forth. So that behavior of having things fall off a cliff, I mean, that's really kind of interesting. Where that might, you might look at that and say, well, where would that impact me? You know, maybe you actually are writing like a web service or something. Maybe this thing is serving up JSON or doing something. Maybe most of the requests are actually fast-running little things. I mean, I'm working on an application like that. They have a lot of little fast requests that run. Those fast requests could be basically backlogged behind some gigantic request if it were doing a lot of CPU work. So if there was some computationally intensive thing, all of a sudden your service would end up behaving kind of flaky, maybe. Like you would get like really poor response time, or it might be kind of a weird lag that's sort of in the system, but it would be hard for you to sort of identify maybe where it's coming from, that kind of thing. So that's what's going on there. It's sort of another lesser known feature of the global interpreter lock is that the thing that basically the effect that it has on response time. Now there are some ways you can deal with that. Okay, I mean it's not totally an all is lost kind of thing. I mean, the typical solution to that would be to maybe throw the work out to a pool, like a process pool or something. So you could say, you know, maybe, well, there's a lot of typing there. Okay, so from the concurrent futures module, you could say, okay, I want to make a pool with maybe, you know, 4 processes in it or something like that. And then what you would do is, instead of just computing the result down here, you would essentially submit the work out to a pool. Okay, so submit it to a pool and then get the result by waiting for the result. If you've never used the concurrent futures module before, it's kind of how it works. You submit jobs out to a process pool, and then you wait for the result. So I'm gonna run that version of the server and just see what happens with that. One kind of negative of doing things with the pool like that is it does introduce way more overhead on the server. It's like the server side, because you're no longer just computing the one Fibonacci number. You're like serializing data, you're sending it off to a sub-process, it's computing a result. So you see that result sort of drop significantly there. But on the other hand, it's not going to be completely hammered by like a CPU-bound request. So if somebody comes in here and they say, yeah, I want to compute the 40th Fibonacci number, that request rate is not really affected by that at this point, because the work is essentially offloaded to somewhere else. You're not fighting with the GIL or anything like that. So that's one of the things you have to think about with threads. If you're going to program with threads, you gotta have to stay away from CPU-bound work. You have to think about pools and other things. But one of the things that you may have heard about is that, well, maybe you just shouldn't use threads. I mean, this is kind of a popular opinion. It's like, yeah, threads suck. It's like, don't do threads. So what I'm going to do is shift gears for a second here, and I'm going to take all that server code. I'm going to just say, let's just abandon threads. Okay, that was a bad idea. Okay, so let's get rid of threads. Okay, hate threads. It's okay. Go back to the original thing here. Okay, and pools. I mean, it's like, we don't want to do pools. I mean, that's kind of okay. So we're gonna go back to the original code, and what I want to look at now is actually this issue of like, well, what would threads buying me in the other one? Like, okay, I was using threads, but why was I using threads? Like, what did threads give me? Essentially, threads were solving the problem of blocking. Okay, so I have all of these operations that block in this code, like waiting for a connection, waiting for data, potentially sending for data. That might happen if like send buffers are full or something like that. But you have these operations that might block, and that blocking is essentially what's preventing the concurrency. I mean, if one of the tasks goes in there and it blocks, I mean, it's like that's the end of the story. It's like, I'm done. Okay, so threads are essentially buying you the ability to block like that, or to stop. I mean, your code is going to run in here, and it's going to hit this statement, and it's just going to stop, and that's like the end of your, it's just going to wait. Now, here's kind of a curious insight about where to go next. It turns out that Python actually does have a feature that blocks like that you have maybe used before, and what it is its generator functions. So a lot of people are familiar with the idea of using generators, maybe to feed for loops. This is a very simple example of that. I mean, the way that this works is if you say, oh, I want to make a countdown, it creates a generator object, and then the way that you feed that is you run it through a for loop, basically customizing iteration. Okay, so this is actually a really cool feature of Python if you've never used that before. But the yield statement, it's really interesting what's happening there, because what happens is that yield essentially makes the function stop until you call next on it. I mean, this is what's underlying the iteration protocol, is that Python just calls next on it a whole bunch of times. Each time you call next, it goes to the yield, and it sort of waits there for a while. So one of the things that you could think about doing is maybe using the yield to do this like blocking idea. So here's an alternate way of running the countdown object here. What I'm going to do is make I'm going to make a queue of tasks using the collections module, and then what I'm going to do is put a bunch of generator functions on there. Like, oh God, okay, what is going on here? Okay, so what I've got is I have a bunch of generators on there, and I'm gonna write a little task scheduler that is essentially just going to do this. It's going to say, well, while there's some tasks to run, I'm going to pop one off, and then I'm just going to run it to the yield statement. I'm going to print out the X so you can see it, and then I'm just going to put it back onto the task list. This is an example of a round-robin scheduler, essentially, if you've ever taken like an operating system class or something like that. So what's happening is it's going to run a generator to the yield, put it back on the task list, and then just sort of cycle around. So what you can do is you can run that, and you're going to see these like 3 countdown functions sort of cycling one after the other, doing like a round-robin thing like that. So if you look at that, you might get this idea where it's like, maybe we could use generators as some kind of task. Maybe we could do a task scheduler or something like that. And the way that you're going to think about this is you're going to go back to this code here, and you're going to look at these blocking operations, and you're going to say, well, maybe I should just yield before that. Okay, I'm going to insert yields into my code. Now I'm going to flesh this out here. I guess flush is not the right. Flesh it out in a second here. So what I'm going to do is put yields into the code because the code might block. I mean, I have to wait for data on a connection. And then what I'm going to do is try to drive this using a generator function kind of idea. Essentially the same thing that I just did. So what I'm going to do is make a task queue. I'm going to make a little run function like that, sort of saying, while there's tasks to run, give me a task. I'm going to essentially run it to the yield statement. Okay, so what this is doing is going to run to the yield. And then I'm going to catch stop iteration, and I'll print, task done there. Okay, so I'm going to start with kind of this task scheduling idea that I just did in the interactive window. It's like, okay, I'm going to cycle a bunch of generator functions out. But here's where it gets interesting. Instead of thinking about iteration, like this countdown thing, that's dumb. I don't care about that. I mean, it's like, why, I'm not caring about like integers and iteration or something like that. But what I'm going to do is I'm going to use the yield statement to communicate sort of the program's intention, if you will. So I'm going to come down here and I'm going to look at this yield and I'm going to say, well, why am I yielding exactly? Okay, the yield is going to make this thing suspend, but why? Like, why am I doing that? Well, in this case, I'm waiting for data to be received. Okay, I'm just going to make it indicate, like, okay, why am I stopping? I'm receiving. Same one here. I'm receiving, and down here, I'm sending. Okay, so I'm going to have the yield kind of indicate, like, okay, what is the intent of this program stopping there? I have to actually do a little bit more than that. I have to indicate, like, well, okay, I'm receiving, but like on what am I receiving? I mean, I can't just say I'm receiving and then give no other information. So I'm going to introduce some other information in here, kind of giving, like, okay, on what am I sending or receiving here? Okay, so I'm going to insert some yield statements in there, and then I'm going to pick those up in this task loop up here. So I'm going to come in here and essentially say, okay, why are you suspending, and on what are you suspending? There's 2 things going on there, and so I'm going to check for that. If you're receiving, okay, I'm going to put some code in there in a second. Okay, so we're going to check for that. If it's something else, I don't know what to do. Okay, so I'm going to have like a check for sort of the receiving and sending, and now what I have to do is sort of figure out what does it actually mean to receive in this context, like what is going on here. So in order to receive, I basically have to go wait. I have to go wait somewhere. Actually, since we're in Canada, this is like going to the penalty box in hockey, essentially. Okay, so if I'm receiving, I'm going to go to the penalty box and hang out. So what's actually going to happen here is you're going to have a waiting area for things that are waiting, and I'm going to have a waiting area for things that are sending. And the idea is that this generator, or this little task scheduler, it's going to say, well, if you're going to receive, I'm actually just going to go shove you into the waiting area, and you're going to go hang out there. It turns out that what I've got here is a dictionary sort of mapping sockets, if you will. It's like sockets to tasks, okay? So, which are generators, okay? So that's what's happening there. So I'm going to make these things sort of hang out, okay? So they're going to go hang out in the waiting area there, and then we have to figure out some way to get them back. We'll get to that in a second here, but let's see what we've got here. Okay, so I have a couple of functions, like the server is using the yield statement, the handler down there, if I want to make the thing run, I'm going to append that as a task, okay? So I'm going to make a task out of it. Actually, let me just run this just to see what happens first, okay? So what's going to happen here is you have this server program. It's going to start off where you have this task list that sort of says, okay, that's this Fibonacci server. It has not started running yet. It's just like, okay, there's some generator. If I ask it to run, you're going to find that the task list is empty. It's like, okay, it did something, but now it's empty. And what's happening now is the task is essentially hanging out in the wait area. Okay, it's in the penalty box, sort of saying, yeah, okay, I'm hanging out. Okay, so that's what's happening. Essentially, that little task scheduler. It's like it ran it once, put it in the waiting area there. And what we've got to do now is we have to figure out how to get it out of there. Okay, so the next thing that we need to do is sort of figure out how do we get things out of the waiting area and back running. So I'm going to make a few changes here. One of the things that I'm going to do is change my loop to essentially run as long as there is any task anywhere just sitting around. Okay, so if any task anywhere in the system is there, I'm going to run. And then I'm going to essentially have another loop in here that sort of says while there are no active tasks to run, I essentially have to wait for I/O. Okay, so I'm going to have to wait for something to happen. Now, the way that you're going to do that, again, your crash course in I/O here, is you can use a library like Python's select library. This is something that lets you pull a whole bunch of sockets at once. So you can do a little thing here where you say, okay, who can receive, who can send. There's a third value that I'm not going to talk about. So I'm going to do a little select thing there. What I'm doing is I'm just pulling the operating system, saying, okay, who can do something, and then whatever I get back from that, I'm going to pop them out of the waiting area and put it back onto the task list. Okay, there's one of them. Let's do the other one. So we have to do one for each of the send and receive there. Okay, so what's going to happen is this little scheduler. You can kind of see it there. It's running a task. It's basically saying, okay, why is it suspending? Going to put it in the waiting area using select, and it gets it back. Okay, so that's the idea. And it turns out that is enough. If I have actually done my work here, that will be enough to get this thing to run concurrent client. Okay, so assuming that there's no mistakes in it, let's check it out. Okay, that's not a good sign when it comes back with nothing there. Oh, I know what's going on there. Okay. You have to launch the child task here. Okay, so it turns out that this is getting completely confused because I did not. I need to, like when I handle a client, I have to put it on the task list. Okay, let's go back to that. Okay, disaster avoided in the demo. Okay, good. Okay, so we have we have that. Let's see if it's working there. Okay, look, that looks good. That looks good too. Okay, so what you've got now is you have concurrency in this system with no threads, using this weird generator yield hack kind of thing there. Okay, so hopefully everybody's mind is not completely destroyed by that. But this is kind of the idea with coroutines is that. Now, one of the things to keep in mind about coroutines is that they are not like an end-all, be-all of like thread problems or anything like that. Like one of the things that can happen is, let's say I run my original performance 1 test on that. You're gonna see that kind of running the same way that it did before. Actually, let me kill that. Okay, I still had like something hammering on the CPU and another thing. Okay, so you see it kind of running the same way. It does not avoid the GIL problem. So if I were to run 2 of these at the same time, you get the same behavior where the time doubles. You're still limited to one CPU core, because I don't have any threads or anything here. I mean, it's like I'm doing everything myself. So it doesn't avoid that problem. It also does not fix the response time problem either. Like if I run that second performance test, it comes up and it's like, okay, 15,000 requests a second. It's a little bit less, by the way, because there's more overhead. I'm doing select, I'm doing all this like generator stuff. Not as much, there's a little bit more overhead on it. But if I were to do like a long-running calculation, like let's go in here and say, okay, I'm going to compute the 40th Fibonacci number. It actually just it's like, well, you're just totally dead at this point. So it's like, I guess since it went from 90 to 0, it's like infinity worse, right? Is that how that works? Okay, so you don't fix that blocking problem, and it turns out in order to fix that, you actually have to go back to the same kinds of the same technique that you had before. A very common thing that you would have to do with coroutines is maybe punt work over to like a thread pool or something like that. I'm going to do a thread pool executor first because I want to say something about that. So what would happen here is you might have to say, okay, I'm going to make a pool of worker threads or something, and then I would have to come down here and punt that work off to a pool to basically get it to run outside the event loop. There's a whole lot of things that are wrong with this, by the way, that we'll get to in a second. Okay, so you would have to do that, basically, send it out to a pool. It turns out that is not going to work. Some of you probably know why it's not going to work, but it turns out if I run this, the performance test again, okay, now it's actually slower because it's using the thread pool. It took a little bit of a hit there, but it doesn't actually fix this problem of the long-running calculation. Like if I go back there, it's like still back down to 0 requests a second. The reason that that's happening is that if you're programming with coroutines, it's basically all in. Like you have to go all coroutines all the way down, and the problem is that this operation here blocks. Like if you don't know whether something blocks or not, that could potentially shut down the whole event loop, and you're sort of back to the original problem. So if you're gonna fix that, there are ways to do it. I'll do it real quick. I mean, one way that you would have to fix it is essentially maybe include more yield statements. You would say, actually, I have to yield because I'm waiting on this future, and you would have to modify the event loop to do something for that. It turns out that the modifications for that are sort of somewhat non-trivial. I mean, what you would have to do is essentially make like a waiting area for the future there, and then you would have to figure out some way to get it out of that. Okay, so you're going to have like a future waiting area for that. The difficulty here is actually getting it out of that. Turns out to be really weird. In the interest of time, I'm just going to code it real fast, and you can all look in amazement or something like that. But then essentially to do that, you have to write kind of a weird callback function that is going to pop something out of there that when it gets triggered, and then I'm going to have to attach that down when this thing gets added. I'm going to have to take the future and add like a completion callback. Okay, so what I'm doing here is I'm essentially adding like a trigger that's sort of saying, okay, when the thing is done, I'm going to take you out of the future waiting area and I'm going to put you back on the task list. It turns out that is even not enough to do it. You have to add some other really weird hack in here as well, which is I'm going to have a future notify and a future event that I'm going to create using a socket pair. And this is like basically an interconnected pair of sockets on your machine. And what I'm going to do is write to one of those. You're like, good God, okay, what's going on here? And then I'm going to have to write like a monitor. You're like, oh God, oh, okay. So that is essentially going to yield that it wants to receive on sort of the future event channel. And then it's just going to read on that, like, and toss it away essentially. And then I have to append that into the event loop. There will be a quiz on this later, by the way. But so what is actually happening there is this event loop is basically stuck on the select, and I have to figure out some way to get it out of there. And the only way to get it out of there is to have like a socket that gets pinged whenever a result gets computed, and then it can wake up the event puller. So doing that, if there are no mistakes in that, I have no. Okay, let's try it out here. Okay, so now we're back to the back to the thread pool thing. If this works, I should be able to do a long-running calculation, and it won't kill the system. Now, it's not impressive, okay? It's still like 29 requests a second. What you're seeing here is actually something really important. A lot of people think that just because you're using coroutines, you can just ignore the GIL. That is not true. I mean, a lot of things with coroutines, you actually have to punt the work over to like a thread pool. If you're using thread pool, all of a sudden you have threads competing with coroutines, and you're back to like square one on that. Okay, so all that stuff with the global, like people who program with coroutines still need to care about the global interpreter a lot. Now I can probably better fix this, if I use like a thread pool or a process pool. So we're kind of back to the the thread version of this. Okay, well, let's try that. Okay, now it's back down to kind of the version with threads because I have to do things in a process. If this works, it shouldn't totally kill that. So it didn't kill that, but I'm having to do the same kind of work. I mean, it's like just because I'm not using threads doesn't mean I have to think about where work takes place and so forth. Now one of the things that I'm going to end with is I want to talk about the programming model of this a little bit. One of the things that you might look at is you would say that yield statement just bugs the hell out of me. Okay, this is cool and everything, but I don't want to put yield statements like that in my code. So one of the things that you might do is you can use a new feature of Python, relatively new feature. I'm gonna make a class that essentially wraps around a socket object and provides an alternate implementation of the receive and send calls. Okay, and you're like, okay, what is going on here? What I'm actually doing is I'm turning that yield stuff into a subroutine, or if you will, or like a hidden behind a method essentially, like that. I'm also going to do this with the accept call. I need to do a yield in front of that. Okay. So what I'm doing is kind of wrapping that, and then I'm going to do a little bit of magic here to wrap that. And no, am I missing something there? Oh, soft data set. Yeah, that's good. I'd probably get infinite recursion or something. Yeah, okay. And then no Python talk is complete without a get attr hack. Okay, so. So I'm gonna do that. What's going on here is I'm essentially making kind of a stand-in for a normal socket, and what that's going to let me do is I can just nuke the yield statement. Okay, I'm going to be able to get rid of the yield. Now, I can't totally get rid of them, but I'm going to change it to sort of a yield from statement. This is the new Python 3 thing from like version 3.2 or something, that you can essentially yield from like a sub-generator or something like that. The underappreciated feature of that is it actually lets you write subroutines that involve the yield statement. Like you can sort of hide behind that. Oh, okay, that's okay. What's going on there? Okay. Weird typo there. Okay, so you can do a sort of yield from on that, and it turns out that will work just fine. At least famous last words. Okay, fine. Let's see if it works. Okay, it's still cranking along. Okay, that's. Okay, look, that looks okay. Okay, so what's happening is you're kind of cleaning up the programming model a little bit. And one of the things that's kind of exciting about that is it takes your code and makes it look almost like thread code. Like if I were to take this code and put it side by side with the thread version of that, assuming that I can pull it up, you're going to find that the two models almost read exactly the same. I mean, one has the yield from, one does not, but from like a logical kind of flow point of view, they look very, very similar. And if you get in, and I guess kind of maybe one of the takeaways is that if you start looking at things like Python's 3 async I/O module, you're going to see this stuff going on. Like if you haven't looked at async I/O, well, when you do look at async I/O, you're going to see a lot of documentation, and it's going to be littered with these yield froms. It's like everything is a yield from, it's like coroutine and so forth. That is actually what they're doing. Now, the code from that is actually written much cleaner than what I just coded. I mean, I was telling somebody in the preparation for this talk that in order to make this fit in 45 minutes, I had to get rid of all good software practice. Like anything involving objects or any good design or anything, like had to go out the window or I would never finish. But I think kind of the point of doing it, though, is just to sort of see, like, what is going on under the covers. Like what is the interaction of the GIL? Like, what is the impact of blocking? What do you have to do to get around that stuff? And so forth. And I think if there's any kind of takeaway on it, maybe I don't think there's any easy answer to that stuff. You have to really think about like what's going on in your application, like how much work is going on in your application, like what work are you going to do where, and so forth. So you're ready to take questions. I guess I'm out of time. I mean, that we can take a few questions, but I mean that's basically the end of that. So we'll see what people think here.
So if I've got any questions, line up in the middle of the room. There's a microphone just there. Let's go ahead.
All right. I think we're good for questions.
Okay.
We'll just start.
Would the multi-processing module help at all with this?
Multi-processing module is essentially the same as like the futures module, like concurrent futures. So it would achieve the same effect essentially.
Okay.
I find the concurrent futures is a little bit easier to work with for this particular, just the way that you do callbacks and stuff is structured a little differently with futures than it is with multi-processing.
Did you experiment with using yield from to actually yield from inside of the Fibonacci generator so that it would break up the work a little bit and keep your requests counter high?
I didn't try that. I mean, the Fibonacci number thing is already so bad. I don't think it needed like additional help there. So.
Did I see an unpacking assignment with an empty list on the left-hand side?
Oh, what that? Did I do that? Oh, maybe I did do that.
Yeah, with the select.
Oh, did I do that with the select?
Yeah, from the select.
Oh, that's interesting.
Yeah, empty list.
That wasn't going to be my question.
Oh, that's really interesting. I wonder why that worked. Where's Raymond Hettinger when we need him here? What I actually meant to do, I have no idea actually. What I meant to do there is do an underscore as a throwaway. That's a trick I often do a lot where it's like, oh, I don't need that. I actually have no. Why would that? Okay, we'll have an open space on an open space. There's at least 5 coordinates. We might have entered like getting the Raymond zone on that. He probably knows.
Next question.
I thought sure.
Yeah, I know it's generalized unpacking, but doesn't it need like a destination, like a? Okay, well, we'll come back to it. Yeah, okay.
If you have an answer for David, come up and ask him after the talk.
Yeah. We'll fiddle around with that. So.
Yeah, I thought the empty list thing was just some incredible next level thing that I was just not capable of. Generally, I felt that way throughout the talk. As an aesthetic experience, this was an incredible talk. It's a sellout crowd, and everyone was on the edge of their seat, dude. I was like really, really feeling it. I really would kind of just want you to pick up where you ended. Actually, my question is. So if it's true that kind of the thread mechanism for concurrency ends, you get to a pattern where you're thinking about how it works and about the load. Does that then call into question, is it possible then to have high-level languages as concurrency becomes more and more acute? Are we back to having to think about the state of the CPU in our high-level logic? Is that where we're going with all this?
I think you have to think about it. I mean, I know for me, there's a lot of like what they call like sort of best practice on concurrency. Like, don't have shared state. use functions, and so forth. And that's how I tend to do a lot of concurrency, is like I have simple functions, there's no shared state. I'm actually thinking more about breaking it up into several, like multiple processes or even multiple machines. Like, if I'm on like Amazon or something, I'm gonna spin up 10 AWS instances, and I'm going to have a bunch of workers kind of dealing with tasks. I can't do that if I have all sorts of thread chaos with like shared state and objects floating around and so forth. So, I think Python works fine for concurrency if you follow the advice of of people who've done a lot of distributed systems and concurrency and so forth. I think the thing to really think about here is that, just going to something like coroutines doesn't end your misery with the gill or something. There were two final comments I did want to make on coroutines. One benefit of coroutines, by the way, is that you can handle a huge number of socket connections in a somewhat efficient way. Like if I needed to have like 50,000 simultaneous clients on this, it's probably more efficient to do that with coroutines than have 50,000 POSIX threads. I could try launching 50,000 threads, but I probably wouldn't want to do that. The other comment is that this little loop here, this select loop, that is actually the core of these event-driven, like callback-based stuff too. Like if you've used Twisted or the callback kinds of approach. It basically, the difference is instead of driving a generator when receiving an event, they trigger a callback function. But otherwise, it's actually, you have to deal with the same mechanisms of like polling, and you have to deal with like coordinating events off of like thread pools and all sorts. A lot of that mechanism is actually the same. So, all right, we're done. I think we're done.
Great. Everybody, please thank David Beazley.
Thank you. All right.
And thank you, the audience. You made it really easy to fit everybody who wanted a seat into a seat. There's more talks in about half an hour, I think. And afternoon tea is down in the expo hall.
All right. Thank you. All right.